Good evening, everyone, and welcome to the Amateur Radio General Class, session number 12. During our previous class, we looked at the Q&A session. We went through the question pool, questions in reference to the theory from the last class. We looked at the topics heterodyning or mixing. We then dealt with the concept of image response, also intermodulation. We discussed multipliers and also deviation and multipliers. We then looked at bandwidth in relation to FM signals. Then we went on to a digital mode known as factor 3. Then we considered what duty cycle was in reference to digital modes. And then symbol rate and bandwidth, the relationship, and then we ended by looking at the concept of noise. In terms of our curriculum, this is where we are. Today we'll be wrapping up the signals and emissions, and we will be able to make a start on the next topic, which is antennas and feed lines. Again, an encouragement to participants to consider taking the practice exams. Links are always up. Feel free. We had no questions from the last class. So we'll proceed now to deal with the question pool review related to the questions that we dealt with for the previous class, the theory associated. Okay, so because we went through all of these theories and so on in detail, we will quickly go through the questions in the question pool. So again, we're just showing you what the actual question looks like in the tests and we're dealing with the correct answer. We are ignoring really the distractor questions or the distractor answers or the wrong answers. Leave that up to you. Everyone has a copy of the full question pool. You can have a look at the wrong answers or the incorrect answers on your own time. So, going straight in. First question, what is another term for the mixing of two radio frequency signals? Straightforward question. Last class, we learned that heterodyning is the term used for mixing. So again, we have to use a fancy term, and that term is heterodyning. Next question in the question pool, and then also to remind participants, the number in bracket or the characters in brackets refer to the question pool number. So if you want to find this question in the question pool, you can search for the number or the characters that appear after the question, and you'll get the full question, including the distractor A, B, C, D answers. What combination of mixers, local oscillator, and RF input frequencies is found in the output? So let's dissect that question. What they're asking us is about the mixer that takes two signals. It takes the signal from a local oscillator and it takes the RF input frequencies. That's the frequency that you're receiving from the antenna, the station that you're listening to, and you're mixing both signals, the RF input and the local oscillator, in the mixer, and they're asking us what is the output from that. Last class we learned that a mixer outputs two signals. It takes the sum and the difference of the two signals. So that's the answer, sum and difference. Next question in the question pool. Which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? So let's dissect this question and see what they're really asking us. So what they're talking about here is tuning a radio. So we have our transceiver or radio and we're tuning a frequency on the dial. 14.240, for instance. We're tuning that, or 14.250. We're tuning the signal on the radio. And we are converting signals of different frequencies. So that's what they mean by tuning. You are tuning a range of frequencies on your radio. Amateur radio transceiver has a receiver that can tune a varying range of frequencies, what we call VFO mode. And that range of frequencies, or those different frequencies, are what we tune to or we vary. And they're asking us which mixer input is varied in order to tune it. So we know one of the mixer inputs is the RF input frequency, and we know the other one is the local oscillator. Again, the previous question also alluded to that when we had diagrams in the previous theory class that shows a mixer takes those two inputs, the radio frequency that you're monitoring and the local oscillator frequency. And it produces, the output is one fixed IF, or the intermediate frequency. Remember we said that about the mixer? The mixer works in such a way that it always outputs the same intermediate frequency. But what is that other input? It's the local oscillator. So you have the local oscillator plus the RF input frequency inside of the mixer, and it outputs the sum and the difference, and it goes to the IF stage. Next question in the question pool. If a receiver mixes a 13.800 megahertz VFO with a 14.255 megahertz received signal to produce a 455 kilohertz intermediate frequency IF signal, what type of interference will a 13.345 megahertz signal produce in the receiver? Okay, I have to take a breath after that question. So it's a very long-winded question. It sounds very complex and complicated, but we did this as a worked example in our previous class. So these numbers may look familiar to you. What they're really asking us here is, if the wrong frequencies mix, what does the receiver produce? Well, the answer to that was a problem. It's problematic when we have this type of receiver, the heterodyne receiver. We get image response. That is the problem that is created when we have two different frequencies that mixes subtraction and addition, or sum and difference, to produce 455. Apart from the frequency that we desire, remember we said one of the frequency was desired and the other one is not desired. So we are desiring 14255 with the local oscillator or VFO that is generating 13.8 to get 455 kilohertz. But when we calculated, we saw that 13.345 megahertz also mixes with 13.8 and produces 455. So what that means is that we are really trying to listen or receive 14.255, but we will also be receiving anything that's on 13.345, the unwanted frequency. And when that happens, that creates image response. So that's all that complicated looking question is asking us. Next question in the question pool. What process combines two signals in a non-linear circuit or connection to produce unwanted spurious outputs? So let's dissect this question a little bit. So they're asking us about a process that happens to combine two signals. But what? The key word here is non-linear. And we learned that if we have something, a mixer that's non-linear, what it will do, it will cause spurious outputs, and that process is called intermodulation. So once you hear non-linear, that should trigger you, okay, it's intermodulation that we are talking about. So that's the link. All right, next question. What is the stage in a VHF FM transmitter that generates a harmonic of a low frequency signal to reach the desired operating frequency? Okay, another complicated sounding question, but let's dissect it and pick out the words that will trigger what the answers that we're looking for. It says, what is the stage? So it's a stage. Is it a mixer stage? Is it an IF stage? Is it a multiplier stage? And so on. What stage in the VHF FM transmitter? So it's not an SSB, it's an FM transmitter that generates a harmonic. There's the key word, harmonic. Another word for harmonic is multiple. So that should give us a little clue. In the question is a clue to the answer. It's asking us about generating a harmonic. A harmonic is a multiple of something. So if you have 2, a harmonic could be 4, and so on, right? So of a lower frequency signal to reach the desired operating frequency. So that's the other clue. We're taking a low frequency and we're trying to multiply it to get to a higher operating frequency. So because they tell us it's an FM signal, it's the harmonic they're asking us about, low frequency, reaching a higher frequency by multiplication, the answer to that question is the multiplier stage does that for us. All right, next question in the question pool. What is the frequency deviation for a 12.210 megahertz reactance modulated oscillator in a 5 kilohertz deviation 146.520 megahertz FM phone transmitter? Whoa, a lot of things inside of there. But what they're really asking us is to calculate deviation. That's what they're asking us. And we learned a formula for deviation, or we learned how to determine what deviation we must apply. Remember we said that when you have a signal that you are multiplying because it's a FM transmitter, and remember we start off with a 12.21 megahertz signal, and then we multiply it to reach 146.52. We just happen to know, we calculated it as a worked example last class, that to go from 12.21 megahertz to 146.52 megahertz, when we multiply, we are using a 12 times multiplier. So to figure that out, all we have to do is divide 146.52 by 12, and we will get, by 12.21, and we will get 12 as the answer. So we know the multiplier is 12. But remember, we have to be careful. The multiplier is also multiplying not only the frequency, but the deviation. So if we start off with a deviation and we multiply it by 12, we will end up 12 times. So for us to work backwards, if we want a deviation of 5 kilohertz in our final transmission, the signal that we originally generate that is going to be multiplied by 12, we have to divide that deviation by 12 to start off with an initial signal that is lower in deviation that gets multiplied by 12. And how do we determine what deviation it's going to be? Well, they tell us the final deviation desired is 5 kilohertz. And we are multiplying by 12. So therefore, to find out what we need to start with to end up with 5 kilohertz, we need to divide 5 by 12 to see what the starting deviation is before we multiply it by 12. So that's the answer. We take the 5 kilohertz deviation that they give us and divide it by 12, which was the multiplier that we worked out when we divided 146.52 by 12.21 to figure out the multiplier. And that becomes 417 hertz. There's a little typo here. They say kilohertz, but it's actually hertz. So just a little typo in the book if you're following. All right, next question in the question pool. What is the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulating frequency? So let's dissect this question. What are they asking us? They're asking us for the total bandwidth. And last class, we learned of a formula to calculate the total bandwidth of an FM transmission. Right? So remember when we hear phone transmission, think voice or you're speaking. That is what it meant by, or is meant by phone transmission. So it's FM phone transmission. We learned that the formula was bandwidth is equal to 2, actually it's here on the screen. It's 2 multiplied by delta F plus FM. And delta F was the deviation, and FM, lowercase f, lowercase m, that is the modulating frequency. Did they give those two parameters to us in the question? Yes, they did. They told us it's 5 kilohertz deviation, that is delta F. See delta F in the formula, and it tells us delta F here is deviation. So we have the delta F, 5 kilohertz. Do they give us FM? Yes, they do. They tell us that the modulating frequency is 3 kilohertz. So we have both delta F and FM. So we plug it into our trusty formula. So it's 5 plus 3, which is 8, multiplied by 2, 16. And that's the answer. Again, we worked this as an example in the last session. Next question in the question pool. What is the approximate bandwidth of a factor 3 signal at maximum data rate? So we did provide that information. It is 2,300 hertz. Right, so next question in the question pool. Why is it important to know the duty cycle of the mode you are using when transmitting? So we discussed that in the last class, what duty cycle was, and we said that some of the digital modes have high duty cycles, and that could exceed the transmitter's average power rating. So you can run the risk of burning out your final transistors in your radio, for example, because of the very high duty cycle. So that's why you need to know the duty cycle of the mode that you're transmitting, so you wouldn't exceed the specifications of your radio equipment. Next question in the question pool. What is the relationship between transmitted symbol rate and bandwidth? So we discussed that also the last class, and we had said that the higher the symbol rate, the higher the bandwidth. So directly proportional. Easy peasy? All right. So let's go again. Why is it good to match receiver bandwidth to the bandwidth of the operating mode? So let's dissect this question. They're asking us, why is it good? Well, it's a good thing. Why do we want to do it? What do we want to do? We want to match the receiver bandwidth to the bandwidth of the operating mode. And we had said that when we do that, we get the lowest or the best, signal to noise ratio, the highest signal to noise ratio, the best signal to noise ratio when we filter out the unwanted information and we focus in, laser focus on the signal that we want to with our receiver, using the mode that we are using. So whatever that mode is, we use the appropriate filter or the appropriate notch or the appropriate receiver bandwidth setting for the mode that we are using. Okay, so someone is asking what page we are on. Presently on the No Nonsense Guide, we are on page 34. Yeah? Okay. So we now go back to our slide deck. Right? And just to let you guys know, I may not have mentioned it before, but at the top of the slide, that just before we go into the question pool, I have the page numbers here. So PP means pages 32 to 34. So a little clue in case I may not have mentioned it before, and you need to know what page if you're following the book. So also the link to the book on Amazon is below. So anyone who wishes to purchase the book, you can go on Amazon and get it. All right, make sure that you get this version for questions between July 2019 and June 2023. There's an older version of the book. Nothing wrong with it, but might as well get the latest version because it has all of the current questions in the question pool. So let's go straight into the theory for today's session. And we are back with digital modes. Again, we dealt with digital modes when we were looking at the technician class, and we're back into more digital modes again. So this time we are talking about PSK 31. We also discussed PSK 31 during our technician class as well. So we are dealing a little more in depth into PSK 31. As we would have discussed several occasions in the technician class, as well as a couple of times in our general class sessions, that whenever we talk about a digital mode, when we say hams or amateur radio operators are using a digital mode, what we simply mean is that we are connecting a computer to a radio to send and receive signals. That is essentially what we're doing. So we have the computer here, and we have some software that's running on the computer, and we may connect directly to a radio, or in some cases, some radios may need an intermediary device called an interface or a terminal node controller, TNC, or an sound card interface. They have different names for it. But some of the modern radios, you have a USB port on the back of the radio, and you can connect it directly to a USB port on a computer, or a serial port if you need to, and so on. So at the end of the day, digital mode, computer operation. Some radios or some transceivers do have built-in functionality to do some of the digital modes, and those are really nice. But think digital mode as a computer interfacing and connecting to your radio, and your radio is sending and receiving signals through an antenna. So that's what we mean by digital modes. PSK 31 is one of those digital modes. We talked about a couple of the digital modes before. Last class, we referenced FT8 as well as Factor 3. In the technician class, I think we talked about GT65. So all those are digital modes, but we're here talking now about PSK 31 as a digital mode that's used very much on HF, the HF bands. And we need to know for exam that it has a transmitted symbol rate of approximately 31 baud. So not hard to remember, because PSK 31, it's approximately 31 baud. So there you go. Easy way to remember it. PSK 31, what's the baud rate? It's 31. And that's relatively slow or relatively low. And just additional information, it's not on the exam, but just for you to know that the bandwidth occupied by a PSK 31 signal is approximately also 31 hertz. Go figure. Now, about PSK 31, we need to know that PSK 31 uses, although it's a digital mode, it uses something called varicode or varicode. It's very efficient, so you can send letters and numbers using that PSK 31 code or encoding using PSK 31, but it uses varicode. And what is varicode? It allows for a variable number of data bits to be sent using a single character. So imagine you send one character and you could actually send a variable number of bits with that one character. And varicode is designed in such a way that the most frequently used characters, frequently used letters, if you remember Wheel of Fortune, you know, is always R, S, T, L, N, and E. Most popular letters, I suppose. That's probably why they choose it in the English alphabet, not sure. But those popularly or regularly used characters use fewer bits, so therefore it's very efficient. It takes less time. All right, so while less frequently used letters or characters will use the other type of characters. So you have the uppercase characters, uppercase letters, for example, which might be less used. They use more bits and they will also take longer to transmit. So the idea is in PSK 31, you would want to use lowercase letters because it will use less time and shorter to transmit. If you use capital letters or uppercase letters, nothing wrong with that when you're doing PSK 31, but it will take longer. So that's why it's helpful for Ham to know this about PSK 31, the fact that it's using varicode, and that the more frequently used letters take less time, use fewer bits, and also uppercase will take more bits and take longer to transmit. And this is a question in the exam that you need to know. And just for your reference, in case anybody wanted to know what are the letters and what are the bits and so on, and convince yourself that lowercase characters use less bits, there you go. You have it. And also, we have a little diagram to show what a PSK 31 signal will look like if you're looking at it on the waterfall. And we'll come to what the waterfall is a little later on in the session. Also, another digital mode that we need to be aware of is RTTY, RTTY, or radio teletype. Now, we did deal with radio teletype during the technician class. We're going to go through RTTY again in the general class because we do have an exam question on it. So, RTTY, radio teletype, it's another digital mode similar to other digital modes. We have GT65, FT8, PSK 31, and so on. And we use a computer in a similar way to the other digital modes. So the story is sounding very familiar. It's a computer connected to a radio. Now, RTTY uses a 5-bit code, and that 5-bit code is the Bordeaux code. Some people will pronounce the word Baudit. They may say Bordeaux. They might even like the place in France called Bordeaux. It's French after the inventor Émile Bordeaux. But it's the Bordeaux code, and it uses 5 bits per character. So you need to know that for the exam. It's a 5-bit character to cater to send the various letters, numbers, and punctuation. But you also need to know for the exam that in addition to those 5 bits, you have an additional start and an additional stop bit. So you have the 5 bits that carry the letter, number, and punctuation, the data itself, but you have a start bit and a stop bit, which you would need to know for the exam. The other thing that you would need to know about RTTY, or RTTY, or radio teletype, is that it uses FSK, frequency shift keying, and you may recall from previous classes what FSK is. If not, just review some of those sessions for a refresher. So RTTY uses FSK to send the ones and the zeros. And we also refer to the ones as a mark, and we refer to the zeros as a space. So these are in your exam, so you need to know it. RTTY, FSK, ones and zeros, or mark and space. And just FYI, PSK 31 and RTTY are what we call general purpose modes. We could use it for rag chewing. Now, rag chewing is a term that we use in the amateur radio or ham radio space to describe chatting, or as we could say in a more formal way, extended informal conversation. But we're really chatting. And we call it, as hams, we are rag chewing. All right? Strange, yeah? Okay, but that's what we're doing. Chewing the rag or rag chewing. Contesting as well, it can be used for, where persons communicate with other hams and try to rack up points to win awards and certificates. DXing, which is long distance exchange of communication, as well as other activities. So that's just FYI. And for FYI again, this is what a RTTY signal looks like on the waterfall. Again, we will be coming up to what the waterfall is a little bit later. Yet another digital mode. And what did we say a digital mode is? We use a computer to connect to a radio. So again, WSPR, Whisper, is Weak Signal Propagation Reporter. That is what WSPR. It's a digital mode, and it is used to find potential propagation opportunities on the various amateur radio bands. So for instance, if I want to go and operate 20 meters right now or 40 meters right now on the HF band, I can go to the Whisper website. So I have the website listed for you at the bottom. Anyone would like to look at it. That's the website on the bottom right. And I can see where signals are coming from and going to. And I can say, yes, there's propagation from Trinidad and Tobago to Europe, or there's propagation from Trinidad and Tobago to the Dominican Republic, or there's propagation from Trinidad and Tobago to the United States, or there's propagation from the United States to Hawaii, or rather United States to New Zealand or Australia. So Whisper is one of those utilities that you can utilize. So it's a mode, it's a digital mode, and hams transmit using this mode. And on the screen, I've actually provided some screenshots of some Whisper transmissions from Trinidad and Tobago, showing where the signals are coming from and where they're being heard. So that is how we can check props or check propagation. And when you see this, you can say, here's what, Europe is wide open. Let me go and try and do some work some stations in Europe, or South America is open, or Africa is open, or the Middle East is open. You know, that's what we do when we are checking potential RF or radio frequency propagation. And Whisper uses periodic beaconing using low power transmissions. At least that's what you need to know for your exam, right? So we are saying it's low power transmissions. We may have, if Franz is online, he may say, wait, Robbie, there are stations that run high power. Well, okay. So, but for the exam, you need to know that Whisper is checking radio propagation using beaconing and low power. Now, beaconing is automatically transmitting a signal. So I will have my computer connected to my radio, and I step away, and that radio will be transmitting automatically because the computer is saying transmit for the next 2 minutes this whisper signal. And I'm away from the radio. So that's beaconing, automatic transmission of that signal. And if you notice here at the top, propagation, did a screenshot. This was actually from today. From a station in Trinidad and Tobago, notice here we have propagation to Australia, 16,000 kilometers. That was just interesting. So in case persons are wondering what is practical, what is real in amateur radio, this is real. These are diagrams from this week, from today, some of them. So note that whisper contains information when the signal is sent, the station's call sign, grid locator, and transmitter power. And the grid locator, really the Maidenhead grid locator, is a code that is used to describe a person's location. It's not latitude, longitude per se, but it's a code that when you see the code, you can map it to your location. And note that the software used for whisper signals can detect very weak signals with very low signal to noise ratios, all the way down to minus 28 dB. And also whisper stations, remember we have a computer that's connected to a radio, connected to an antenna. Well, that computer could be connected to the internet. So that station, whisper station, receiving whisper signals can submit or upload those reception reports to databases such as WhisperNet as well as PSK Reporter. Those are two websites that aggregators that collect signal reports and allow you to display the parts like I'm showing you here on the screen, bottom right-hand corner. You're actually seeing a map, and this is from the WhisperNet website, whispernet.org. So you can check that out as well. So folks, we will take a short break at this time, 2 minutes. Get up, take a stretch, have a bathroom break, have some water, and meet you right back. Okay, welcome back everyone. All right, so for the question that was asked during the break, I'm using the electronic copy of the No Nonsense Guide. So if you purchase the printed copy, sometimes when persons or publisher prints a book, the page numbering might be different. So you may have to follow by the section headings. So the topic, just follow the topic and hopefully you could locate it. All right, so I'll bear that in mind as well. So just to wrap up on Whisper. So we said Whisper is a digital mode. And just the word whisper, how we pronounce WSPR, just remember it's low power transmission, or it ought to be low power because we are whispering. All right. So another digital mode or technology used for digital modes will be packet radio. And we need to be familiar with the concept of a header in packet radio. So packet radio is a form of switching technology used in digital modes, such as APRS, which we would have come across in the technician class sessions, as well as PACTOR. The data is transmitted from one station to another via something called packets. And a packet radio frame, which is what we need to know for our exam, includes the following. And we need to pay attention to the header. And what the header has is not the actual payload or the actual data to be sent. It's really routing information on how to handle the content. And that is information that the computers will use to decide where to send it next, what to do with it, and so on. So in a packet radio frame, there's the header. So you need to know about the header, what the header is for the exam, and it handles information on the content as well as how to route the packet. So there's a visual here that shows at a very high level what a frame looks like, a packet radio frame. And notice that there's this thing called the header. And the header is separate and apart from the content or the information, or what we sometimes refer to as the payload. So it's extra information called the header, and it tells the computer how to handle the information, how to route this packet. You need to know that for the exam. So digital modes such as PACTOR and WinMore, those are two of the modes, digital modes that exist or that's used by AMs or used by amateur radio operators. But PACTOR is a very robust type of digital mode. It does use packet radio technology, and it extends internet functionality for remote users via amateur radio. So email, for instance, is one of the things that could be sent over PACTOR. And for the exam, we need to know that PACTOR incorporates error correction as part of the protocol. Apart from detecting errors, there is something called a NAC response, or NAK, NAC. And no, it has nothing to do with the Raymond Ramrino, Delina, and so NACing. It's NAC, NAK. It actually really means negative acknowledgement. So that NAC is the request that will ask for the data or the packet to be retransmitted or resent. And that is the powerful feature that makes these protocols robust. It allows for the error to be addressed by saying, please retransmit, I didn't get it, or I didn't get it correctly, or I didn't get it. So that is how the errors are corrected, by sending a NAC, which tells the sender, please send that information back. Or in radio, we'll say again. Now, there are limits to asking for things over and over, right? So that's the point we're making here in the third bullet point. There are limits to requesting the retransmission excessively. So, I mean, how many times could you say again? You know, you're talking to someone, maybe on the telephone. What did you say? What did you say? After a while, you're going to give up. 3, 4, 5, 10 times. You know, it's like you get fed up and you know what? I'm going to give up. And that's exactly what the data modes do as well. They are going to give up eventually. And that failure will cause the connection to be dropped. And that also applies to PACTOR, as well as the other similar protocol called WinMore. It's another protocol used by hams to send email, for instance, to one another using something called WinLink. And we would have talked a bit about WinLink on a previous session. WinLink is used to send and receive email over radio links. Yes, it can be integrated with the internet, but you can send radio to radio, or you can send radio to a relay station that will relay it onto the internet. So it's very useful for disaster type situations where you may have lost internet yourself, but you may have radio and you could send your radio signal, let's say through HF to another country, and that country will have a gateway that sends it on to the internet for you. So that's how you can send email to everyone. Now there's another method for handling errors, and it's called ARQ. So that's another automatic repeat request. That is another feature for handling errors in these digital modes. So you need to know that for the exam. And what ARQ do is it requests the packet to be retransmitted. Automatic repeat request, ARQ. So yet another capability with some digital modes. It's called forward error correction. So the whole idea is a signal may go across a radio wave, some means, and reach a destination, but there may be noise, it may be corrupted. But guess what? We have the ability to do error correction. So apart from knowing that an error occurred, which is error detection, there's the ability to correct the error. Yes, you can. So FEC, forward error correction, is another means by which some of the digital modes deal with errors. Now, not all digital modes, just some. But if the digital mode that you're using has FEC, it will add to the robustness, because included in the packet that is sent with the information is additional information, or what we call redundant information, that allows the receiver to correct the error using the redundant data or the extra data. And the diagram at the bottom here tries to illustrate that. So this is the information we're trying to send, these yellow pieces, this yellow bit of information here. And notice on the receiver side, they receive all of it. But what happens on the source side, it takes this data and adds additional information. So even though this is all that we really want to send, we send all of this. It has redundant or extra information, and all of it is sent, but not all of it makes its way across. But enough of it makes its way across so you could reconstruct what the original is. So that is what is meant by forward error correction using redundant data in the packet. The receiver doesn't have to ask back for the packet because it contained an error and didn't get it. They use whatever information that they got, and as long as it's sufficient, they can reconstruct the original data, and that is called FEC, forward error correction. And that redundant data is transmitted and included in the same packet. So the redundant data, just FYI, while it helps us to correct errors that may occur without retransmitting, note that that extra information included in the packet, remember you're starting with just this bit of information that you're seeing on the screen, but you're actually sending all of this by the time it goes on to the air. So you're sending extra stuff. Therefore, you're taking up valuable space and time. And therefore, as a result of all that extra overhead, you end up with a reduced data rate because you're sending extra stuff that technically you don't need, but you're sending it as insurance to make sure that it gets to the other side. But it's a disadvantage because it slows the otherwise rate that you could have used that information to convey. So it's a bit of a disadvantage, as great as it is. So again, we have emphasized the point that digital modes use a computer, and a computer will run software. So some examples of software that we use in amateur radio. So a couple of the modes we talked about PSK31. The name of the software that we use is called FLDigi. That's one of the applications that we can use. And for FT8, we have looked at this before, WSJT software. Also, part of the software includes something called the waterfall display. So a couple of the previous slides, we showed some pictures like the one on the bottom right-hand side there. So we're coming to the point where we are describing what the waterfall display is. The next slide, I'll show you a bigger picture of the WSJT software and its waterfall display. But for now, a waterfall display provides a visual representation that shows the following. And again, you need to know this for the exam. The waterfall display will show the signal strength, and the signal strength will be indicated by the intensity of the color that you see in the waterfall. The frequency as well, you will see it on the horizontal scale of the waterfall. And the time, or as time elapses or time passes, that goes on the vertical scale. Again, these points here are part of the exam, but it'll probably become a little more apparent what we mean by the signal strength is shown by the intensity, and the frequency is on the horizontal scale, and the time is on the vertical scale when we come to the next slide that actually shows a bigger picture showing what the WSGT software is and the waterfall. The thing about the waterfall is when you look at it, you can see the activity on a band visually. So you don't have to tune across the band and say, is there something on this frequency? Let me tune up the road. Is there something on this frequency? No, you see a wide range of frequencies other than the one that you happen to be listening to. And you can see, hey, look, just adjacent, higher up, there's another transmission that's occurring. Let me tune to it. So it allows you to quickly tune to that station by selecting that signal on the waterfall. Also, you can tell the quality of the signal by looking at the waterfall. So for example, and you need to know this for your exam as well, if a station is overmodulating, you will see vertical lines on either side of the signal. So there's a picture representation of what that might look like. So you need to know this for the exam. If a station is overmodulating, you can visually see it, especially for digital modes. You may not want to be listening to it. Your computer is decoding. But if you look at the waterfall, you'll see if they are overmodulating. So I did promise you we'll have a bigger picture or screenshot of what the WSGTX software looks like, and specifically the area of it called the waterfall. So you have all of this information here, but we are focused in on this section that's bordered by the this box here. This here towards the bottom is our waterfall. And each of these columns is actually a different transmission that is being received. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to stop counting. There are dozens of signals here in that little piece of spectrum. So notice we had said, what did we say? We said the signal strength by the intensity. So if you were to look at this one here, this signal here, you notice a lot of reds, very strong intensity. You'll notice this signal here is very weak. So as the color is more intense, you get yellows into the reds, more intense colors, stronger signal, such as this signal is a bit stronger. This signal is a bit stronger. You're seeing a lot of yellow and even getting to red. But notice this signal here, very weak. What about this signal here? Hardly even there. It's a signal. It will be picked up by the software, but it's super weak. So that's what we mean by the first point, that the signal strength of the transmission will be indicated by the intensity of the waterfall. And so look at this signal, very strong, very, very strong signals, very, very strong. Almost no signal here. There might be a signal, but it's so weak we can't even see it. But some weak signals inside of here. Look at this relatively weak signal. Weak signal here too. Weak signal. Hardly anything at all. Strong signal. Very strong signal. Strong signal. Strong signal. So the intensity. So I hope I've convinced you that the intensity indicates the signal strength. What did they tell us as well? The frequency is on the horizontal scale. Let's prove that. So here's the frequency. 500, 1000, 1500. That's the frequency. So horizontal scale shows us the frequency. Now, if you could see it, you may not be able to see it too clearly, but there's a time here, 21:58 hours, 21:57 hours. So that's why we say the vertical scale is time. So more recent signal is on the top, and the waterfall flows downwards. It flows, so it moves. It's not static. This is why we call it a waterfall, because it moves downward with time. So time is on the vertical scale, and that's the point that they've made here in these bullet points. WSGT software and waterfall display. Okay, so as amateur radio operators, as hams, some of the spectrum that we get to use as a licensed service, we share, and some frequencies we are primary, meaning that we are exclusive to it. We have the priority on it, and we are the only users, or to be the only users. But that is not so for all. We share the spectrum with other users, and we refer to that as hams being secondary. When we have exclusive use, we say that we are primary on the band. So just note that when you get your amateur radio license, not all of the spectrum is allocated to you on a primary or exclusive basis. As hams, you may share it with another service. And therefore, we say we share the spectrum, and that's where we are secondary. So you need to know this as a ham. And this is an exam question that we do share some of the spectrum. One such example where we share the spectrum. So you may be familiar with Wi-Fi signals. Now, there are a couple of different bands for Wi-Fi. You have the 2.4 gigahertz band, and you also have the 5 gigahertz band. But we're talking here about the 2.4 gigahertz band. That is called the ISM band. It's an unlicensed band. It's ISM simply means industrial, scientific, and medical. But that 2.4 gigahertz band, part of it is shared with hams. Hams could operate on that band, and just below that band, there's a piece that hams have exclusive use of. So hams share that part of what we call the 13 centimeter band, 2.4 gigahertz, with other services such as Wi-Fi. As a matter of fact, hams do use commercial repurposed Wi-Fi equipment because we could run higher power, we can use another part of the spectrum that commercial operators cannot, and you have additional privileges and less restrictions. So for example, you could use the additional bandwidth as a licensed ham. You have to stay within your license, of course. You can't use bandwidth that you don't have license for, and you could run a higher transmit power as per the authority providing you with those power limits. So hams do use that band. And on the right hand side here is an example of hams using that spectrum, Wi-Fi spectrum, and part that the hams have to do what you call a mesh network, very high speed. And two examples of those networks are the HSMM, also known as broadband hamnet, and AREDN, sometimes pronounced ARDN. Okay, next topic. We talked about feed lines before in the technician class, but we are getting a little deeper. So one of the types of feed line that we looked at was called twin line, twin lead, ladder line, and there are several other names that could be used to describe. But we are going to talk about this type of feed line because remember, feed line is what connects your antenna to your receiver, your transmitter. And there's a characteristic about the feed line that we need to be aware of. It's called the characteristic impedance. And we need to know about impedance, which we have learned during our course. We also need to know what is the specification of the impedance. The reason that we need to know that is because, remember we said hams are matchmakers? Well, we'll come to that in a little while, a little further. We need to match things. But how do we determine what is the impedance or the characteristic impedance of a feed line? What determines it? So for the feed line that we have displayed here on your screen, there are two factors that we need to know for the exam that determines the characteristic impedance. The first one is the distance between the centers of the conductors. And the second will be the radius of the conductors. So let's dissect that a little bit using the diagram that we have below. So if we were to look on the right-hand side, this is a ladder line, for instance. You have two parallel conductors. This in the center here really is just a separator. All that is doing is just keeping the wires apart. That's its function. But the transmission really is going over these two wires or these two lines. So there's a distance between the two wires, and this is what is represented here. So this is a cross-sectional view of this ladder line. You have the two wires, the first wire, you have the second wire, and this is the center line of this wire, and this here is the center line, and we are noticing that we have a distance between the centers. That's why the first bullet point is the first factor is the distance between the center of the conductors. So this is the center of this conductor, this is the center of the other conductor, and this D, big D, is the distance between the center of the two conductors. So if you need to visualize what distance between the center of the conductors are, this is it. And also, the radius of the conductor. So what is the radius here? Small d, the radius of this conductor. What is its radius? And this is what we need to know for the exam. For feed line characteristic impedance for this type of line, it's the distance and the radius. So we come to another type of feed line, coaxial cable or coax. We came across this, or we would have dealt with this during the technician class. Coax cable or coaxial cable is actually the most common type of cable that you will find amateur radio operators use. It's the most common antenna feed line. So between your antenna and your transceiver, between your antenna and your radio, coax cable is the most popular type of feed line that is used. And we need to know for the exam that the characteristic impedance of coax used by hams is 50 ohms. But also note that 75 ohm cable is used from time to time, not very often, but in your exam they will ask you what's the characteristic impedance of coaxial cable used by hams or amateur radio operators, and you need to know it's both 50 and 75 ohms. But 50 ohms is the most popular, and the reason why is because most amateur radio transmitters have an output impedance of 50 ohms. And remember we said hams are matchmakers, so if we have a transmitter whose output impedance is 50 ohms, then we need a transmission line that connects to the transmitter that is also 50 ohms. The antennas used by hams, the impedance at the feed point of the antenna is also close to 50 ohms. So 50 ohms, 50 ohms, 50 ohms. Hams are matchmakers, so we try to use 50 ohms right through. Just bear in mind the little note here that sometimes hams will also use 75 ohm feed line. Again, don't get confused when you see that in the exam. You say, well, Robbie said 50 ohms is what is typically used. Yes, that is true. But 75 ohms can and is used also. And you will see that in your exam. Okay. So we're coming to the end of today's class. This is our final slide for today. And we need to discuss feed lines and the concept of mismatch and reflection. So remember we said hams are matchmakers, but what if we don't do a good job of matchmaking? Well, that can happen, it does happen, and it happens a lot. So even though we are matchmakers, we have a lot of issues making that match. So any difference between the feed line impedance that we are using between our transceiver or radio on our antenna and the impedance of the antenna at the feed point will cause some of the transmitter output power to be reflected back towards the transmitter. And that's not a good thing. So let's dissect that a little bit. So this is our transmitter that's going to be transmitting output power, 100 watts, whatever it is, forward to the antenna. And this is the antenna feed point. So my radio is connected to my antenna through our trusty feed line, and that is 50 ohm coax cable perhaps, and I'm transmitting at 100 watts going forward. But guess what? My antenna feed line, the point here is not 50 ohms exact, and therefore I have a mismatch. And when that happens, some of that power is wasted and is sent back down the transmission line as reflected power, just because I have not matched this feed line properly to the antenna 50 ohms, some of it is coming back down. It's not a proper match at all. And that is problematic. It's not a good thing. But of course, there is some amount of reflection. It's just that you don't want a lot of reflection. You can have problems with too much reflection, the least of which is your signal may not go anywhere, because why would you want to transmit using your transceiver, your radio, send a lot of power forward to your antenna? You want that power to go out into space. You want it to leave your antenna and go bounce off the ionosphere and go to another country, maybe Croatia. We're trying to communicate with a ham in Croatia. But guess what? Because the feed point of the antenna is not matched with the impedance of the transmission line, guess what's happening? A lot of my signal will be reflected back, wasted. It doesn't go out of the antenna. Why would I want to waste that? What's also worse, if it's a lot, that reflected power could result in heat being created extra heat in my radio, and I could probably burn out my final transistors. Very important components and very expensive components. Why would I want to do that? So hams out matchmakers, when we aim to match the feed point impedance of the antenna with the transmission line. So we say here that for efficiency and effectiveness and to avoid damage to equipment, the ideal case is to have all of the transmitter out power go to and be radiated by this antenna. That's what we want, with very little being reflected as far as possible down to the transmitter. So again, hams are matchmakers, or at least we try to be. So folks, we have come to the end of today's session. Thank you so much for being part of it. And yes, I'll take this question quickly there, Ian. Yes, you can adjust the impedance of many antennas. Some antennas is fixed, but many antennas, there's an adjustment. Sometimes you call it a gamma match. There are things that you can do. And if you can't match the antenna directly, as we spoke of in a previous class, you can use an antenna tuner if you must. But the answer is yes. Quite often you can. Sometimes you shorten the antenna, you lengthen the antenna, you add some capacitance. There are several things that you can do to adjust the impedance of an antenna. So very good question there, Ian. So again, any concepts that we might have covered before that's unclear, for the persons who have recently joined the class, we're still getting new joins. Please check out the technician class material, because a lot of what we do here builds on that. And this is the link for our session from the previous level called the technician level. And so folks, certainly we'd like to thank everyone who attended last Wednesday's webinar, practical radio operating tips. If you missed it and interested, again, it was optional for persons in the class, but we saw quite a lot of persons from the class. So thank you so much for your support and attending. Hopefully it was helpful. And persons who might have missed it, or anyone that would like to review it or miss part of it, there's the link here. This URL contains a recording from Wednesday's session. So our next session, God's willing, will be next Friday. I believe it is the 2nd of July. Usual start time, 8:30 p.m. So thank you so much, everyone. Continue to be safe. Do have a great weekend. All the best. Take good care. Okay, Adesh, thanks very much. Ramzan, good evening as well. Okay, Roger, good evening to you as well. Jessica, all the best. All right, so Ramzan, we'll try and see if we could synchronize what page number on the printed book to I'm using the electronic book, so there may be a mismatch from the PDF. Okay, Ian, cool. Adesh, thanks again. All the best. God bless to you too. Adrian, you're certainly welcome. All the best. All right, Ramzan, have a good night. Okay, George. No, not sure if when the local exams are scheduled, but as we indicated before, remote exams are always available online. Okay, Gary, good night as well. Take good care. Thanks, George. You too. Sleep tight. Okay, Roger, you too. Have a restful night. Take good care. You too, Sylvester. God bless as well. Have a good one. You are certainly welcome, Marissa. Thanks. You be safe too. Eustace, have a good night also. Take good care. Anthony, greetings as well. Thanks so much. All the best. Sure, Ian. Certainly a pleasure as well. And glad to know that you're enjoying it. Take good care as well. Okay, Kevin. Have a good night. Or should I say Lamek? Thanks a lot, man. Take good care. Appreciate it. Okay, Nickel, good night as well. Thanks very much. Take good care.